Have you ever looked at a mountain of complex data, brain scans, sensor readings, protein structures, and thought, how do I even begin to make sense of this? Not just analyze it, but truly understand it. Well, the answer might not lie in more computing power. It lies in geometry. Not the flat, two-dimensional kind you learned in school, but the kind that bends, curves, and folds in ways that mirror the true nature of real-world data. Welcome to the world of Riemannian geometry, a mathematical universe where space itself is curved, and where the tools we use to analyze data must evolve with it. Because here's the truth, most real-world data doesn't live on flat planes. It lives on manifolds, curved, high-dimensional surfaces that encode structure in ways flat models simply can't capture. Think of it like this. When you map the Earth onto a flat piece of paper, Greenland looks huge. But it's not. The distortion comes from forcing a sphere into a plane. Now imagine trying to average brain scans, classify textures, or cluster robot movements, each of which lives on a curved space. If you force them into flat space, you distort reality. Take functional MRI data. Each brain scan produces a symmetric positive definite, SPD, matrix, a mathematical object that describes how different brain regions activate together. These matrices don't lie on a flat grid. They live on a curved manifold, a space where distances and averages behave differently than in Euclidean geometry. And that's where the real challenge begins. How do you cluster, average, or compare data when the space itself is curved? Traditional methods like k-means assume flatness. They break down here. You can't just take an average by adding matrices and dividing by 2. Because on a curved space, the average isn't a simple arithmetic mean. It's a point that minimizes the sum of squared geodesic distances, shortest paths along the surface. This is the domain of Riemannian geometric statistics, a framework pioneered by researchers like Xavier Pennock, which allows us to do things like compute intrinsic means, define geodesic distances, and build barycentric subspaces. Essentially, the average shape of a group of brains or the center of a cluster of textures. And here's the key insight. Some curved spaces are especially well-behaved. Take Hadamard manifolds, spaces with non-positive curvature like a saddle. In these, every pair of points has a unique shortest path, and averages are stable and well-defined. That's why they're so useful in medical imaging, where we want to compute a typical brain structure across patients, without the distortions that come from flat approximations. But even within these well-behaved spaces, traditional clustering methods like intrinsic k-means can be painfully slow. Why? Because at every iteration, the algorithm must compute geodesics and update centroids on the curved surface. Each step involves expensive numerical optimization, like hiking uphill and downhill over and over again to find the center of a mountain range. And when you're dealing with thousands of brain scans or high-dimensional textures, this becomes impractical. So how do we solve it? Enter Fréchet Map Clustering, FMC, a breakthrough that rethinks the entire approach. Instead of working directly on the curved manifold, FMC embeds the data into a flat Euclidean space, preserving the most important relationships, using something called the Fréchet map. Here's how it works. Pick a few reference points, landmarks on the manifold. For each data point, compute its distance to each of these landmarks. These distances become a new coordinate vector in flat space. So a brain scan that was once a 100 times 100 matrix becomes a list of numbers, say 3.2, 5.1, 1.7, 4, 8, and suddenly you're in flat space. And now, you can apply standard k-means clustering, fast, simple, and battle-tested. The result? Speed. In real-world tests, FMC was 14 times faster than intrinsic k-means, cutting runtime from over 800 seconds to just 58 seconds on 4,000 brain-like data points. And it wasn't just fast, it was accurate. In texture classification, sorting cotton, wood, foil, FMC was 25 times faster than traditional methods while matching their precision. But here's the clever twist. How you choose the reference points matters. Random placement leads to poor embeddings. So researchers developed a smart heuristic. First, use a rough approximation to estimate cluster positions. Then place reference points outside the cluster if clusters are far apart, between them if they're close. This ensures the flat map preserves the separation, so when you cluster in Euclidean space, the results make sense. And unlike older methods like Log-Euclidean, which assume data is near the origin and fail when points are far away, FMC is robust. It doesn't rely on a central anchor. It adapts. This isn't just a faster algorithm. It's a paradigm shift, a way of thinking. Don't fight the curvature. Use it to flatten just enough to solve the problem. So to recap, real data often lives on curved manifolds, like SPD matrices, brain connectivity, or rotation spaces. Traditional clustering fails there, too slow, too unstable. Fréchet map clustering solves this by embedding data into flat space via distance-to-reference point maps. Then apply fast, standard k-means. Result: blazing speed. High accuracy. Robustness. It's like giving data science a superpower, the ability to find meaning in complexity without drowning in math. This isn't just about one algorithm. It's about a new way of seeing data, not as numbers but as shapes. Not as signals but as geometric objects. From brain scans to protein folding, from autonomous vehicles to financial networks, this is the future of data science, geometry-aware analysis. Because when the data curves, the tools must too. If you're fascinated by how math reveals hidden structure in the world around us, hit like, subscribe, and let me know what kind of complex data you'd love to explore next. Because the world is full of shapes, and someone's got to understand them.